The islands of the Lesser Antilles are home to 3.2 million people. Let's investigate the tectonics and earthquakes of the subduction zone along that margin of the Caribbean plate. The Caribbean plate moves east at about 2 centimeters per year with respect to the North and South American plates. There is essentially no relative motion and no earthquake zone marking the boundary between the North and South American plates in this region. So we will informally refer to the plate subducting along the Lesser Antilles subduction zone as the Atlantic plate. As that oceanic lithosphere dives beneath the Caribbean plate, it produces earthquakes of increasing depth from east to west across the subduction zone. Ocean bottom seismometer observations have refined plate tectonic cross-sections, and these contours show the depth to the top of the subducting plate. Also of note is that volcanoes are located above the point where the top of the subducting plate reaches 100 to 150 kilometers depth. In the northern part of the subduction zone, the Atlantic plate subducts to about 150 kilometers depth beneath the volcanic arc that lies 300 kilometers from the trench. The accretionary prism of sediment scraped off the subducting plate onto the overriding plate is about 5 kilometers thick. Near the southern part of the Lesser Antilles Trench, where the Orinoco River sheds sediment from the South American continent, the Atlantic plate carries the sediment load, many kilometers thick, towards the trench. Oceanic lithosphere subducts at a shallow angle in this region, where distance from the trench to the volcanic arc is 460 kilometers. The accretionary prism is nearly 20 kilometers thick due to the sediment load delivered to the trench and piled onto the Caribbean plate. Now, let's dig into the earthquake history. In January 1843, over 120,000 people lived on the island of Guadalupe. On February 8th, the largest earthquake on record shook the region. All masonry structures in Puerto Pietra were destroyed, resulting in 4,000 to 6,000 fatalities. This event illustrates the difficulty of interpreting patterns of earthquake intensity from written accounts of ground shaking and damage, than inferring earthquake properties without seismometer recordings. For example, some researchers developed intensity maps with isoseismal zones elongated parallel to the trench, and inferred the Guadalupe earthquake was a magnitude 8 or larger plate boundary megathrust earthquake. Lack of tsunami indicated that the rupture did not reach the ocean floor. But other researchers developed intensity maps with a smaller area of violent intensity shaking with more circular isoseismal zones. Without knowing how deep the earthquake was, this intensity pattern could indicate several possibilities. Was it a shallow magnitude 7.5 within the overriding plate? Was it a magnitude 8 plate boundary megathrust? Or was it a larger event within the subducting plate? So it's not clear whether that earthquake was a plate boundary megathrust event. Since 1950, 4 major earthquakes have occurred within the subducting plate. These events were mostly due to extension within the upper part of the subducting plate as it bends into the subduction zone. Depth to the hypocenter below inhabited islands resulted in low human impact. In 1974, a magnitude 7.2 earthquake occurred northwest of Antigua, producing the strongest shaking in the Lesser Antilles since 1843. Because the epicenter was nearly 20 kilometers from Antigua and about 25 kilometers deep, there were no fatalities, though some damage occurred to buildings and port facilities. As the Lesser Antilles Trench curves from north-northwest to east-west where it meets the Puerto Rico Trench, the Atlantic plate subducts at an increasingly oblique angle. Resulting trench parallel forces produced the Bunce Fault, an 850-kilometer-long strike-slip fault that transports a sliver of accretionary prism along the trench. This structure was named for Betty Bunce, a pioneering marine geophysicist who was the first American woman to serve as chief scientist on a major oceanographic expedition. Marine geophysics and seismicity indicate the northern forearc of the Lesser Antilles is broken by normal faults. The Antigua earthquake occurred on one of these normal faults that pose earthquake and tsunami hazards to the region. With only 5 major earthquakes in the past 70 years, and perhaps no great megathrust earthquakes in the past 200 years, the unusually low seismicity here has puzzled seismologists for decades. GPS observations can now monitor subduction zone deformation. Most examples, like Japan or Alaska, have a high-friction megathrust fault that is stuck for decades or centuries, compressing and pushing the overriding plate backwards. When forces eventually exceed friction, an earthquake releases the stored elastic energy in a major magnitude 7 or great magnitude 8 or magnitude 9 earthquake. GPS observations reveal different dynamics for the Lesser Antilles subduction zone. GPS stations on the islands show little motion, indicating that the Caribbean plate is not being compressed or pushed back as the Atlantic plate subducts. Instead, the low-friction megathrust boundary slips more smoothly, with fewer earthquakes and perhaps without great magnitude 8 or 9 earthquakes. Although the dynamics of the plate boundary are complex and a topic of ongoing research, two factors are likely to contribute to low friction on the Lesser Antilles megathrust. The Atlantic plate is old, cold, and dense where it enters the subduction zone. It's pulled down by gravity, essentially free-falling into the deeper mantle, so frictional coupling along the boundary is very low. Additionally, oceanic crust formed at a slow spreading ridge, like the Atlantic plate, contains hydrated minerals that release fluids as the subducting plate warms. These fluids can further decrease friction along this plate boundary. So, great megathrust earthquakes and the resulting tsunamis may be extremely rare or entirely absent in the Lesser Antilles. This does not mean there is no tsunami hazard. The Great Lisbon earthquake of 1755 killed over 50,000 people from building collapse, fires, and a tsunami. And that tsunami crossed the Atlantic in 7 hours and, without warning, swept southward across the island arc with run-ups from 7 meters at Ceiba to 1.5 meters at Barbados. The largest historic tsunami of regional tectonic origin was produced by the 1867 magnitude 7.2 earthquake in the Anegada Passage. Even at Grenada, tsunami run-up reached 3 meters. In terms of natural hazards, volcanic eruptions and hurricanes in the Lesser Antilles have been far more deadly historically than have earthquakes or tsunamis. In 1900, the town of Saint-Pierre on Martinique was a bustling seaport. The catastrophic eruption of Mont Pelee in 1902 killed 30,000 people in a matter of minutes when a pyroclastic flow barreled down the mountain, burying the town. Volcanic activity also presents tsunami hazards from explosions, landslides, and collapse of volcano flanks, displacing ocean water. The Great Hurricane of 1780 pounded across the Lesser Antilles with wind speeds as high as 320 kilometers per hour, killing over 22,000 people, making it the deadliest hurricane in recorded history in the Atlantic. Whereas modern weather observations and modeling provide warnings that save lives and mitigate storm damage, hurricanes remain a deadly and costly natural hazard in the Lesser Antilles. Though less frequent than hurricanes, major earthquakes can occur anywhere in the Lesser Antilles with no warning. Protective actions like drop, cover, and hold on should still be understood by all who live in or visit this region.